In 1977, the Gossamer Condor won the Kremler Prize by being the first human-powered aircraft to complete a prescribed figure-8 course around two turning points a half-mile apart, determine the lift and coefficient, and the power required by the pilot. And so here are the characteristics of the Condor. It flew at 15 feet per second, had a span of 96 feet, a chord of 7.5 feet. Its coefficient of drag was 0.046. The powertrain efficiency was 0.8. And the weight, and this included the pilot, was 210 pounds. So the Gossamer Condor is an interesting plane. And this is what it looked like flying. Now, you can actually see this in the Smithsonian. They do have it at the Air and Space Museum up in the rafters on the second floor over by the exhibit that has the World War II planes. Crazy stuff. So the Kremler Prize is kind of like the X Prize in the 70s. So they made this human-powered vehicle. And so now let's go determine everything. So let's first start with the lift coefficient. So how do we determine the lift coefficient? Well, the coefficient of lift is going to be the lift force divided by rho over 2 v squared area planform. And since we are flying, we are going to know that the weight has to equal the lift. So that's for steady flight. And we can get that from our free body diagram. This is our plane. And there's our weight that has to equal our lift, which we're given in the problem. The weight, including the pilot's 210 pounds. So we can go and calculate out the coefficient of lift. And so I'm going to flip this 2 on the top because it's 1 over 1/2, which is the same thing as 2. So 2 times the weight, 210 pounds, divided by the density. And typical air density is 2.38 times 10 to the negative third slugs per cubic foot. We have the velocity squared. The problem tells us that we are moving along at 15 feet per second. And then the planform area, that's going to be the span times the chord. So if I multiply 96 by 7.5, I'll have 720 feet squared. And so now we look at this, and this should be completely unitless. So a pound is the same thing as a slug foot per second squared. There's our slugs, go away. We have velocity squared, and I caught that because my units were not calculating out correctly. So there is a foot cubed. Take one of those. The second one will cancel out up there. Second squared, cancel second squared. Everything cancels out, which is great. So if I calculate out my coefficient of lift, it's going to be 1.09. So on a side note, we'll talk about lift to drag ratios, or when you're talking about aerodynamics, lift to drag ratios, and really is kind of a measure of, it's an informal measure of how efficient something is. So 1.09 lift ratio, 0.46 drag ratio. That gives a lift to drag ratio of 23.7, which is really impressive. A 747, that big huge Boeing plane, has a lift to drag ratio of about 17. So we're a much more efficient than that. Okay, and so the next thing is we want to know what's the power required by the pilot. So we need to overcome drag. So to overcome drag, it's the power times the efficiency, velocity times the drag force. Okay, so we have the efficiency as given in the problem. We have the velocity. We have to calculate out the drag force, but we do have the coefficient of drag. So if I rearrange this equation, I've got the power times, how do I calculate out the drag force? Because remember, coefficient of drag is going to be the drag force divided by rho over 2 v squared a star. And in this case, because basically the entire plane is that lifting body, we'll be using the planform area for calculating out the drag. So if I end up rewriting this a little bit, To get the drag force, I've got 1/2, or let's just do it right as rho over 2, velocity squared, planform area, times the coefficient of drag. That gives me my drag force, times the velocity from my equation here, and then I'm going to divide that by the powertrain efficiency. And so we can just say that's velocity cubed in there. So now we'll go 2.38 times 10 to the negative third slugs per foot cubed, and then multiplied by 1/2, velocity cubed, 15 feet per second cubed, coefficient of drag, which was given as 0.046, and we're going to divide that by our efficiency, which is 0.8. And so if I calculate that all together, we're going to need to worry about the units. And so slugs per cubic feet, once again, slugs are a pound-foot per second squared. And so let's start looking at things and how they cancel out. Actually, that's a mistake there. Slug is, so we go back here, 1 pound is a slug foot per second squared, so that means a slug would be a pound second squared per foot. Cubic feet cancel out. Second squared, second cubed is, we'll have a 1/2. And so, wait, the units aren't working out right. Oh, I forgot my planform area. And once again, this is where it's good to look at the units because you'll catch things like this. So our planform area is 720 square feet. So now we'll have the foot here, cancel out the foot there, or we'll get the right units because now I'll have pound foot per second. So that's 166 foot-pounds per second. Let's convert that over into horsepower. So 1 horsepower is 550 foot-pounds per second. And so that tells us that the person that was pedaling the bike to drive the Gossamer Condor was putting in 0.302 horsepower into the system to fly it.